This is lecture 2, part C, and I noticed there's 15 slides here, and I'm going to go ahead and break this into 2 so I don't have to rush. So anyway, the issue of this is, or the topic is memory mapping, and the idea is we're going to take smaller memories and make larger memories out of them. So we want to move towards doing that. So this is typically, I think it supports kind of understanding of a lot of digital topics, and let's look at these things. Yeah, so to be able to do this, you really need to understand binary numbers, understand basic hardware associated with memory and some other elements, as particularly standard decoders, as we'll get there, and also just memory addressing in general. So you need to understand how just generic memories work. So we'll kind of be thinking that these are RAMs in here. Typically speaking, they'll have some extra features on them, such as tri-states, to get these working, and we'll talk about those when we're getting there. So this is actually a very useful topic, has a lot of stuff involved in it. It's kind of weird the first time you see it, but it shouldn't be too bad if you start working with it. And the good thing is that there is a ton of support for these problems in the text. So the solutions are out there. So take a look. So this is the a table I chopped out of the book, and I always say these are numbers that you should know. You should have these numbers memorized. And essentially it's related to, it's just binary numbers all over again, but it's related to the number of address bits in a memory. So this is the idea here is, if I have this many address bits in a memory, like a RAM, this is going to be the decimal range of that associated memory, and this is binary. This is hexadecimal range. So, for example, if I have 1 bit, I can have 2 different things. Because 2 to the 1 is 2. Those 2 addresses are 0 and 1. That's extreme case. But anyway, if I had 8 address lines, which is this case right here, 2 to the 8th would be 256. I have the possibility of storing 256 different things. The addresses are 0 through 255. Now the issue in this thing is, it's always, the decimal range is always 0 through 2 to the n minus 1. So this is 2 to the 8th minus 1 is 255. This is very nicely represented with hexadecimal. Binary gets kind of unwieldy. But if you look at this pattern here, it's like a repeating pattern. Any of these ranges here goes from this many zeros to this many ones. So, for example, 2 to the 8th goes from 8 zeros to 8 ones, which is, here's the hexadecimal range here. 8 zeros through 8 ones is 0 to 255, which is 256 different things. Okay, so once again, this is the number. This is relating the storage and the addresses to essentially a memory such as this. Remember, this M here is the number of address lines, which is essentially this column here. So I typically, for the most part, have all these numbers memorized just out of usage, and this is something you absolutely should memorize. You're going to memorize it anyway, out of use, but essentially up 1 through 8 you need to memorize, and certainly a very popular one is 2 to the 16th, which is 0 through 65536. Now this is a memory map example where what I want to do here is take a 264 by 8 and make it into a 128 by 8 memory. And what I want to do here is write the addresses in for it. And so I'll do it with the easy one. Let's see if this is working. Then the examples on the next page here. So essentially what I'm going to do is say, gee, it's 64. So I'm going to go back to the last slide and see that 64 is related to, 0 through 63, that's what I'm looking at. It's related to 6 address bits. I know that range is 6 zeros through 6 ones, so I can go back and look at this, and I'm going to put that in there, 0, and that's 8. So let's get rid of that, and this through 1 1 1 1 1 1 1. Too used to writing 8. So 0 1 1 1 1 1 1. Okay, so the notion here is that the range for each of these devices, I'll make it look a little clearer. Put it in groups of 4. The range for each of these 64 by 8 devices is 6 zeros through 6 ones. So the difference between these two, the way I'm going to differentiate these when I put it in a circuit, I'm going to call this kind of the zero memory, and this is the 1 memory. So in the end, what I have here is these two ranges here, 7 zeros through 1 0 with 6 ones, etc., etc. The whole range for this thing is 7 zeros through 7 ones, but in between here I can put the mapping of these devices, and that's the important part. So the same idea for this memory here. I'm going to say 8K. So I'm going to go back to the previous slide and say 8K. It's this thing. That's 2 to the 13th. That's 13 address lines. And 13 address lines for each of these devices. I'm going to say 1 2 3 4 2 3 4 1 2. I don't want to write all these 1. Okay, for this one device, that's the address range. Okay, each of these 4 devices will have the same address range. The way I'm going to differentiate these is, because I have 4 of them, I'm going to call this one the 0 0, the 0 1 1 0, and 1 1. You'll see that in the next slide. So this is what I was drawing by hand on the last slide. This is 6 zeros plus 1 0. There's 6 ones plus the 0. So once again, this is the 0 memory. This is the 1 memory. So this same here. This is all these are the same. You can see this column the same. It's differentiated. It's differentiated by. Let's get this drawing here. It's differentiated by that column right there, and you can see it 0 0 0 1 1 0 1 1. Okay, that's how I'm going to differentiate these memories when I need to. So what we're getting into is extending these memories, essentially making bigger memories from smaller memories. So there's 2 things we can do here for these problems. We can extend the data width, or we can extend the address space. So or we can do both. Okay, so we're not going to do both in these problems. What you'll see is extending the data width is absolutely no big deal. Where it gets interesting is extending the address space. And so that's all. I'm going to go ahead and break it here and start the next video with these problems. So once again, what I'm moving towards here is to be able to create larger effective memories from just essentially smaller memories.